Okay, so thanks for joining, guys. So today we are going to discuss a new chapter, which is ROS Slam. Uh, I know we have two more chapter. I actually planned with this chapter, but I think for getting a fresh start, I think the ROS Slam chapter is much better. Compared to the Path Planner. Path Planner is mainly programming, but uh, the ROSLAM is about um like different mapping techniques, and we can see some demonstration. So there is not much programming involved, only just configurations. Okay, so maybe I can start with what Islam is. So I just before the session I just searched like Slam robotics or what is Slam. So do you guys heard about Slam algorithm in robotics, guys? Slam algorithm? Anyone? Anyone heard about Slam before? Maybe I think you may heard about Slam, maybe, but I don't know you work with Slam before. So maybe I can start with the intro. What is actually Slam? So the best example that I can use is the self-driving cars. Okay, self-driving cars. Um, okay. So in self-driving cars, you know self-driving car. What is a self-driving car is, right? So it's basically going from A to B. Like there is no driver. We can just give the destination. So the robot will bring you to that position. Okay, to that position. So how is that possible? How is that possible? Without any prior understanding about the environment, is that possible? No, right? It's not possible because, like human, robots are not intelligent by nature. I mean, we have to artificially create the intelligence, right? So in that aspect, this algorithm called SLAM algorithm, it stands for simultaneous localization and mapping. So this algorithm in robots, especially in self-driving car, which is actually the hottest area now, right? Which is applicable. This SLAM is applicable for almost all the robots, like a wheel robot, drones, then legged robot. Uh, all the robot it is applicable, but I'm actually talking about the relevance. Like self-driving cars, actually the hot area. Um, so in order to create the map of the environment, we are using a technique called SLAM. Okay, mapping. So maybe I can show you a mapping self-driving cars. Yeah. Uh, you can see this image, right? Yeah. So here you can find the robot is actually in the center, okay, and you can see a 3D map around the robot. 3D map, actually the rings around the robot is actually the velodyne, the lidar. But what about these 3D structure? These 3D structure, I mean 3D. Yeah, it's actually point cloud, okay, but it's actually a map. Okay, it's a 3D point cloud map. Okay, so how can we create that? It's a question, right? Like, just imagine you are inside a self-driving car, and you actually given a destination. So the destination can be any place. Okay, any place. So how this is possible? Like, how can a robot can create the map, the 3D map of the environment? So the thing is that uh, before driving the robot, okay, before driving the robot autonomously, before making the robot autonomously, uh, one of the first approach is to create the map of the environment. Okay, so you may be thinking like the self-driving cars are like, I mean, moving without understanding the environment around it. But that is actually wrong. The self-driving cars actually need the prior understanding, and so before going from A to B, it should map the environment. Okay, and we need the 3D mapping, not the 2D mapping, because the environment actually is 3D, right? So we need the 3D mapping. There are many algorithms for mapping. One of the set of algorithm is called SLAM, simultaneous localization and mapping. So this technique can help you to map the environment in 2D and 3D. Okay, it's based on the sensors and algorithms that we are using. So SLAM is a very big topic. So if you search for SLAM algorithms, you can find a tons of algorithms actually. Okay, SLAM is actually the technique SLAM, and under the SLAM algorithm there is visual SLAM, and there are many different SLAM algorithms available. Okay, and if you are doing like PhD or masters, a lot of people are researching on SLAM. Okay, because in order to map an unknown environment, okay, we can use SLAM with an exploration algorithm. So I think I have shown you the DARPA challenge, right? Subterranean DARPA challenge. So this was one of the this was one of the challenge which actually test a lot of SLAM algorithm. Why? Because one of the challenge is happening inside an underground tunnel and caves. So you can see here. So this is a challenging environment in the competition. Okay, so there is a tunnel, and there is an urban environment. There is a cave. Okay, it's actually a concept, but it's a cave. Okay, so the competition is basically mapping all these things. Okay, but you can think about the complexity. Inside the cave, we can't able to control the robot. You will not get the Wi-Fi. You will not get even, assistance is also very difficult. Like even human can't go through these caves. It's very difficult. That's why they organize this challenge, because one of the importance of robotics, or one of the challenge that robots solve, is that robots can solve some tasks that human can't able to, or humans are afraid of doing something like that. So like if you want, if a human wants to go to some complex cave, there is a risk involved, right? But for robot, it's like, even if the robot dies, it dies. Okay, only the money matters. But if a human travels through this cave, the life actually matters, right? So that's why we are deploying robots. So in order to map these complex environment, we are using SLAM algorithm and also some exploration based algorithm. Exploration, what do you mean by exploration? Exploration, I think from the word itself, we are simply exploring unknown areas, right? Humans are very interested in exploring unknown places. Likewise, robot is having exploratory algorithm, so it can keep on exploring the unknown areas and keep on mapping it using SLAM. Okay, so I think you got the relevance of this topic, the SLAM topic. So it is using extensively in robotics, and there are a lot of research works happening in SLAM. Mainly, I have seen a lot of SLAM based project while I was doing research assistance in CMU. So they were been working on drones. Okay, and it was using drones and lidars. Okay, that's a main area they have been working on. So drones will go through some caves or some area, and it will map the 3D environment, something like that. Okay, so that is the relevance of SLAM, which is mainly using for mapping the environment, and not only mapping, at the same time it can localize the position. on the map. For example, uh, the robot is actually moving in an unknown area. So while it is moving, it's actually creating a map. Okay, and at the same time, it is actually localizing means it is having an estimate where is the robot position with respect to the map. Okay, so that is what the SLAM algorithms are about. Okay, so there are a list of SLAM algorithms, 2D SLAM, 3D SLAM, or visual SLAM. Visual SLAM is working on the point cloud. I think I have shown you um, the 3D point cloud that is around the self-driving cars, right? So this is kind of visual SLAM. Okay, so I think you got an idea about at least an abstract idea about what is SLAM. Okay, so what is SLAM about? So that is the SLAM concept, and if you simply search it, you can find some good examples. Good definitions of SLAM. Okay, so there is a question from Tejas: 2D versus 3D versus VSLAM, which is the preferred and why? So Tejas, it's actually depend on the application. So I think I have mentioned that in the self-driving cars, uh, we have to prefer the 3D SLAM because uh, we are mainly working on the point cloud, and yeah, it's actually, the environment is very very big, right? And there are a lot of features. So with only 2D map, we can't able to do the navigation. So maybe we need maybe both, a combination of both, a 2D map as well as 3D map, and also some vision assistance will help to navigate. Okay, so that should be required for complete self-driving, or full self-driving mode. Okay, so these are the main um, challenges that we are trying to solve in robotics. Okay, and if we are working on like indoor robots or like very small, with some simple purpose like going from A to B in an indoor environment, maybe 2D SLAM will be preferred. Okay, but if it is very complex, if the environment is very complex, then 3D you can prefer. Okay, Tejas, I think that can help. Okay, yeah. So yeah, so I think we discuss about the SLAM. So I'm just sharing some links. Some random links from Google. This is from MATLAB. So yeah.
You are using a SLAM. What are the basic inputs to the only the camera, or it is any lidar and sensors, radars also?
Yeah, so
What you locally?
that is depending on the type of SLAM that we are using, and that's what we are covering next. So what are the different types of SLAM? We are going to cover that. So maybe I can simply mention like, um, so for doing the SLAM algorithm, performing the SLAM algorithm, we need a set of input for sure, right? So there are different sensors available, and maybe I will say we have to use the odometry data from that is a wheel encoder feedback, then lidar. If it is a 3D SLAM, we have to use the 3D depth sensors or velodyne kind of 3D lidars. So it's a combination of these kind of sensor based on the type of SLAM. So I can talk about the input and output. Maybe after, while discussing the different SLAM algorithm. Okay, so this is actually like the relevance of SLAM. I was talking about what is SLAM. It's actually a technique that we can use it for mapping and localization, and why it is important. I was just talking about like in self-driving cars and all. In order to navigate from A to B, we need some kind of algorithms like SLAM. Okay, so now I am coming to maybe to the explanation how the SLAM works. Maybe we already seen this image, right? So I think this will be a better illustration of SLAM. So I hope you can able to see the image. Okay, so the SLAM algorithm will take some inputs from the robot. Okay, so the inputs are like the local pose and global pose. Mainly it is taking the local pose. Okay, local pose in the sense, if your robot, it can be a mobile robot, or I mean any kind of robot, if it is having a position feedback, like the if you if imagine a wheel robot, and it is having odometry wheel encoders, and it can provide the wheel odometry, it can compute the wheel odometry, for example. So this wheel odometry, or the pose, local pose of the robot, can be used in SLAM. Okay, that is one input to the SLAM algorithm. Okay, because SLAM algorithm need the current pose of the robot. Okay, it can be from wheel encoders or from IMU or anything using a sensor fusion. So the odometry can be one input. And next is the important sensors, that is the LiDAR. Okay, LiDAR can be 2D as well as 3D. So if you are working on simple indoor robots project, then there are set of 2D LiDARs available. 2D LiDARs in the sense, these LiDARs actually rotate. Mostly the LiDARs are 360-degree LiDARs. So it will rotate its own axis, and it can give you the range values around the robot, so like obstacles around the robot basically. Okay, so if you fit a 360-degree LiDAR on the top of the robot, then you can find the obstacle around the robot 360-degree. Okay, so this obstacle profile, or the range values around the robot, is again the second input to the robot. Robot SLAM. Okay, so first was the odometry. For some algorithm, odometry is not used. In some algorithm, odometry is used, and in some 2D SLAM algorithm, LiDARs are used, and in 3D SLAM algorithm, 3D LiDARs are used. 3D LiDARs, I think I already demonstrated it before. The Velodyne, it can give you a 3D data around the robot. Okay, so this is self-driving cars, and you can see the difference between a 2D LiDARs and 3D LiDAR, right? 2D LiDAR data is like this in a plane, and in 3D LiDAR is actually we are getting 360-degree data only, but in 3D. Okay, so so the input can vary according to the type of SLAM. Okay, and rather than these sensors, there is visual SLAM, which is mainly using camera input. Okay, camera, and there is visual SLAM with the camera and laser scan. Okay, it's a combination of that, and you can create SLAM algorithm based on multiple sensors. For example, if you have multiple LiDARs, you can actually input to the SLAM. Okay, so yeah, there is a question, what is pose graph? So visual SLAM uses RGBD data. Yeah, so I am coming back to that point, Tejas. So so these are the set of sensors. Okay, so for the visual SLAM, we are using cameras. There are cameras like normal cameras we can use, or stereo cam, or depth camera. I think you have seen the real sense and all, right? So RealSense can output the RGBD data. Okay, RGB is the colored image with the depth information. Okay, so these kind of sensors that we can use as the input to the SLAM. Okay, and also we can use IMU. Okay, IMU as the input to the SLAM. So I think you can understand, right? Based on the type of SLAM, you can use a combination of sensors. But the majority of the sensor that we are using is like encoders, camera, lidars, IMU, all the. I mean, these are the main sensors that is used in robot anyway. Okay, so that is the input. And then, so what is these sensors actually gives? These sensors are giving the obstacle profile around the robot. Okay, mostly the lidars mostly. Even the camera can give you the obstacle around it and the features as well. Okay, the features like corners, all these things that the camera can give you. And yeah, so using these features, it can estimate the motion and also it can create a profile of obstacle. Okay, and using these data, no, they using these data, you can calculate the motion, and from that we are generating a kind of post graph. I'm not sure you have heard about um, there is a library actually. I I think post graph library in C++, graph slam. Okay. Okay. Uh, Let me check. That is actually a popular library, Postgraph, I think. Yeah, Postgraph. Okay, let me check. C++ library. I actually forgot the name, but actually I have attended a talk of this. I mean, author of this graph library. So that's what I was searching. Yeah. Anyway, leave it. So the post graph, no. Maybe I can just go back to, yeah. So what happening is that when the robot moves, okay, when the robot moves, the sensor data, all the sensor data is changing. So Tejas is having a question. Yeah, okay, is it an HDL graph slam? No, Tejas. I was not looking for the slam, but the library. There's, I think it's Postgraph or something. Postgraph or something. Or from the HDL graph slam, maybe I will get the library that is using no there was a library in, I mean, that is actually the backend of these kind of slams. So that was, I was searching. Okay, anyway, leave it. I can share later. I think it's Postgraph or something. So yeah. So these motion estimations are taken from the sensors to the front end, and then what happening is that these I mean pose is actually putting in a graph. Okay, putting in a graph means it's actually a data structure. You can put each nodes into it. Okay, I think graph, I think it's not graph, data structure. Yeah, it is having nodes and all. Um, yeah, graph data structure. Yeah, like each features will be like keep on putting in inside the graph. Okay, so that's how, if you work with Slam before, these changes, like when you maybe I can show you a video, Slam video ROS or something, um, G mapping. um, yeah, I think we can just see this. Yeah, let me just go to the visualization. Yeah, so you can see here, here they are simply showing a Slam algorithm. I think it's G mapping. It's I mean G mapping package. So you can see when the robot moves, uh, it actually hold the map. I mean, when the robot moves, the odometry actually changes, the laser scan data is getting updated, and from that, the front end actually calculating the motion things and all. And you can see whenever the robot moves, it actually holding the map, and also the robot pose as well. Robot pose is actually with respect to the created map. So in order to hold this kind of data, okay, we are using the one of the approaches, the graph data structure. Okay, so there is a famous library in C++ that is actually using by modern Slam algorithm. Okay, I actually attended a talk of the author because there is a famous company called Skydio. I will get back to that after this. So in order to hold the changes in the map, we are mainly using the graph data structure. Okay, graph data structure, and that is actually converted into the map. Okay, like the map that you have seen here. So there are a lot of processing happening, taking the sensors data, then motion estimation, registering on the graph. Okay, so this can't be same for all the graph, I mean Slam algorithm. It can be for graph slams mainly, the Slam algorithm that is using the graph, I mean graph of as the main data structure, I think. Okay, so I actually mentioned the post graph because there is a company called Skydio. Okay, I'm not sure you have heard about it. Anyone heard about Skydio, guys? Skydio. Okay, so this is an interesting company, guys. So maybe, yeah, drone company, yes. So why I mention this, because these guys actually started the autonomous drones for filmography. Okay, and it's awesome actually. Maybe let me just um, just show some demonstration. I'm not sure. Yeah, you can see here, this is one latest video, I think. So for drones, using drones, one of the problem that most of us are facing is that, like, if you plan to scan some area, okay, then it will be manually operated. Mostly the inspections and also the mapping will be manually operated. Okay, so like in order to inspect some bridges or something, there should be a person who is controlling, and there can be accidents for sure. Okay, so using Skydio, no, Skydio is an autonomous drone, and the thing is that you can simply mark the area that you want to scan. Okay, this is a new application they have created. So just mark the area, and then Skydio can autonomously map the surrounding. So there is no need of manual operator. So how Skydio is doing it? I mean, it's using some SLAM techniques, and I mean, image stitching and all this operation. I think the drone is creating the map. So you can see Skydio build a 3D map, okay, and you can see like it can detect all these objects, okay, and create the map of it. Okay, so one of the key contributor of this technology was the author of the postgraph, or the library that I have mentioned. Okay, so um, it can autonomously do the filmography in some better angles. So you have seen the action shots in some movies, right? So Skydio can perform better than that. Okay, so that is Skydio, and I can show you the film. That is also interesting. Yeah, this one actually released before 4 years. This was the first USB of this company. That is the first model. It was Skydio R1, and I work with this drone actually. So it is actually good. Like, just start the drone, okay? Just start the drone and start the app on your mobile, and then you can just move. You can just run it. Then the drone will be tracking you. You can see. I mean, it's not only tracking you; it's actually filming you. Okay, and you can see how complex it is. Okay, I'm appreciating this technology because these guys are from MIT. They actually worked I think many years to mature, to make this technology. I mean, not just for making, to mature it. So you can imagine how complex it is. So you can see here, the uh, Skydio drone is actually creating a map of the surrounding in real time. Okay, and using that map, it's basically the voxel grid map, and using that, it can uh, create a plan. Okay, create a plan through this map. Okay, through this map, and it can avoid the obstacle. Here is another video. He's the founder of the Skydio, and we can see some nice. This was the first project, autonomous helicopter, that they created in MIT. So it can go in very fast pace. You can see here. I think it's happening on the yeah um, parking space. So it's moving very fastly. And here is Skydio, the product, and yeah, it can perform much better than that. Okay, you can see some visualization. That's what I was trying to show you. Yeah, I think, see, there are cameras around it. Okay, there is the drone is perfectly working using camera. There is no lidars. All using the I think 12 cameras basically. Okay, all cameras are fisheye cameras. Fisheye means there will be distortion. So with that distortion itself, it can able to create the 3D point cloud. Okay, so within this very challenging environment, they are creating the 3D voxel and try to create a path. Okay, the planner is the next challenging part, and it can, I mean, track the people and film them. So this is the internal representation of the see, the robot is actually navigating with these complex point cloud, and is creating the trajectory in real time. Okay, so I was just saying about the importance of SLAM and the algorithm and the latest stuff happening. um, yeah So there is a question from Tejas. Yeah, computer board. The computer board is TX1, TK1. I mean, currently is TX2. NVIDIA. It's not the board actually. Maybe if you just search Skydia NVIDIA, you can get. It's powered by Jetson, and they're actually not using the board and all. They're simply taking the SoC. Okay, it's using the TX2, but you can find it's handling 12 cameras. Yeah, so Kalpesh is pointing to G2O. Let me check. I think. Um, Let me check. OpenSlam G2O. No, no, not this. This is actually, I think, this is mainly, I mean, seems like an old one, but it will work fine. But there is a latest algorithm which is actually powering this Skydio. So that's what I was trying to convey. G2O, I think it will work, but this library is the backend, the library that I am talking about. So you can find the Skydio is simply powering with one TX2 chip, and it is taking care of all the SLAM, then control, and all the communication with the ground station. Okay, yes, this TX2 is handling. So that's where the optimization comes. So just a second, let me clear. Just okay. So like I don't know like the moon landing theory, moon landing whether it's hoax or not, but you can just imagine we actually used I think 20 megahertz or 25 megahertz. I mean, it's very less megahertz processor for landing in the moon. Okay, landing in the moon. But if you check the current computer configuration, it's actually running in octa core or 16 core with tons of RAM. Okay, and what we are basically doing is we are filling the computer with Chrome tabs, right? So just imagine like with 16 megahertz that can able to land the moon, but with 16 GB of RAM we can only fill the RAM with the bunch of Chrome tabs. So that is a situation. So I mentioned this thing. Why? Because to point out the importance of optimization. I'm not very aware of the optimization techniques and all. I think I learned something, but this is one of the I mean complex area. I mean software optimization. It comes mathematical optimization is also a part. I mean it can come in the algorithm level. So optimizing means if you want to run a software on a computer, you can optimize it, and then optimization can help you to reduce the computing power, but without sacrificing any performance. Okay, so you can check like the Skydio example. They are doing everything within a small footprint. Okay, this is only the footprint in the sense it has to include the battery, it has to include the I mean processor, then the board, and at least you can see we need some cables, right, to connect to the rotors and also cameras. So everything is in this miniature form. Okay, and also it's not very costly. It's not very costly. I think it's around, yeah, the starter kit actually like less than $1,000, and the complete kit pro kit is actually less than $2,000, but it's actually very less. I mean, when compared with the technology. Okay, so that's what the optimization comes. So when you are doing a product, this kind of optimization can help you in terms of cost. Okay, so like when you optimize the software, the optimization can happen in the hardware and software both. But if you optimize the software, you can reduce the computation. If you reduce the computation, you can I mean, downgrade your processor, because you don't need much bigger or powerful processor for running your algorithm. So then obviously reduce the cost. Okay, the NVIDIA Savior uh, is one of the board. I think you all know. It's actually cost around 85K in India. Okay, it's more than that actually, different models. So just imagine you are using an 85K and currently it's 2,74,000. So just imagine for 32 GB. So if you are putting a board like this in a product, how costlier it will be? Okay, how costlier it will be. So if you can reduce the computation, we can maybe switch into some cheap alternative of it. Okay, so that's where the optimization plays. Yeah, so I was just like saying about these things, so let me close all these things. Okay, so I was just talking about the slam graph, the backend part, and also the optimizations. Okay, maybe we can jump into like the different kinds of slam, or what are the list of slam available, and what are the slams available in ROS. Okay, so the list of slam I'm not taking because there are a lot of slams available. But if you just search for ROS slam, I think we will get a bunch of algorithm. So what do you mean by ROS slam? Uh, just a second. Um, yeah, I think this is actually my book. Okay, maybe let me check if there is any list of slam. Gazebo, I mean, yeah. So maybe I can show you, no problem. So ROS slam, in the sense, there are different slam algorithm which is actually written in C++ and Python. I will say most of the slam algorithm will be written in C++ because um, in slam algorithm we need lot of optimization to make, lot of performance to be considered. Okay, so the C++ will be the best choice for creating this kind of stuff. Okay, so you can find different packages, like packages in the sense library for doing slam. So one of the library is OpenSlam. I'm not sure how many of you visited this website before. So OpenSlam is actually a slam algorithm implementation, which is called FastSlam. FastSlam. Okay, FastSlam. So the paper actually mentioned here. This is one of the oldest slam algorithm available, but it will work very well as well. Okay, so OpenSlam is the implementation of FastSlam. So I can give you an idea of FastSlam. Yes, Rohan, I'm continuing recording. Continue recording. Yeah. So the FastSlam is actually one of the oldest one, and you can find the author. Uh, just take this paper, and can you identify these guys? I mean, any of these guys, authors from the authors list. Can you identify any popular figure? So it's basically created in Carnegie Mellon and Stanford. So one of the professor is very famous now. Can you find it? Anyone heard about? Yeah. So yeah,
Sebastian.
it's the Sebastian Trun. So he is the founder of Udacity, and also he actually started the self-driving car revolution. I will say. Okay, so he is actually the author of FastLab. Yeah, so one of the author. uh, there is a famous book actually, Probabilistic Robotics. I have the ebook copy actually. Just a second. We can say it is the Bible for the navigation, SLAM, localization, and everything. Okay, so these are the three popular figures who are extensively worked on SLAM, localization, and everything related navigation. And so Sebastian Tran, Wolfram, Dieter Fox. Okay, Sebastian, I think he's still the founder of Udacity, and Wolfram, actually he joined in Toyota or something. He's in my network, and I have actually met Wolfram in some conferences. I have some pictures with him, and Dieter Fox. I think he's in Nvidia now. Okay, so this book, the Probabilistic Robotics, these guys actually started. Okay, Sebastian Trun is one of the author of FastLab, and this is the backend of the famous package in ROS called G mapping. Okay, so like I can do a comparison. So we are working on this package in ROS, and the backend of this package is the FastLab. Okay, or there is a package called OpenSlam. Okay, which is written in C++. So this OpenSlam actually, I mean, wrapped in a ROS package. So that is the G mapping. So this is the famous SLAM package available now. Okay, so I just want to compare this thing and this thing. Okay, so I'm not sure like if some of you work with ROS, and if you done some mapping and all, don't think that you are an expert in robotics. I mean, that is actually can happen because you will think like doing a navigation or mapping using ROS. I mean, you are in very high level. Don't think like that, because the work, the complexity of robotics are in the algorithm level. So for implementing this kind of mapping, SLAM, everything, you can see the algorithm here. So this algorithm you can't able to copy. You can maybe refer to the past papers, but this is actually created by their own idea. And this is where the complexity or the difficulty in robotics comes. Okay, so when you start working on robotics, you can be in the implementation level, or you can work as an engineer. So if you are working in an engineer level, then it is mandatory to know the different packages in ROS, so that if your employer, or if your professor, or I mean if your client wants to do some mapping with the robot, you can simply take this package and you can implement it. Okay, so myself, I am considering me as a engineer, so I'm not I mean a kind of research person, because like maybe it's my limitation, I don't know, uh, but it's very difficult. I mean, it's not for everyone. Okay, but I'm not discouraging you, but if you have that I mean um, that will for doing this kind of high-end research, then work for it. So I mean, make your max stronger, and you have to keep on reading multiple papers in this domain. Okay, so that's how if you are planning to do PhD, especially in PhD, you have to keep on reading the papers and keep on improving yourself, otherwise you can't able to create this kind of work. Okay, I think this paper created, they have written 20 years before or something, but it's still relevant. Okay, so just check the equations. Even I'm not able to I mean able to understand what's going on. Okay, so this is a simple um, slam algorithm. So just think about the complex visual slam or 3D slam that we are using in the self-driving cars. Okay, so I think you got an idea, right? This is actually not a simple thing. The background, I mean, the back end of the SLAM algorithm is pretty complicated, and yeah, so you can see it's published in 2000 or something, 2000. So it's been 22 years. Okay, so this is considered as a base paper for the SLAM algorithm, and inside this book, I think most of the things around about the mapping, you can see the table of contents. Mapping, localization, planning, and control is covered. Okay, so if you want to focus into SLAM, uh, this is your Bible. Okay, and
Is it possible to download it or
yeah,
it's
actually
available? Or
it is illegal, but yeah, it is available in some I mean pirated websites, but I think if you plan to buy it, then I think it's somewhat expensive, I guess. Um let me check the Indian price. Yeah, the hardcover is actually like 6,000 rupees, and Kindle version is 4,000. So it's somewhat expensive, and it's a bigger. It's a very big one. Like how many pages? I think 672 pages. I think, yeah, it's actually bigger. I mean, yeah, 1 kg and 360 gram. Okay, so 672 pages. So it's one of the reference if you want to focus on to the slam area. Okay, yes, and I can show you the pioneers in this field. Dieter Fox, I think he is in Nvidia. Let me check. um, yeah, I think he was in Nvidia, but currently, yeah, I think he's a professor and also doing work in Nvidia. Okay, he's the director of robotic research in Nvidia, so you can just imagine. Okay, and this is his Google Scholar. Search index is 119. He's in University of Washington and Nvidia. Okay, having citation around 82,000. Yeah, and the next is Sebastian Trun and Wolfram Burgard. So Sebastian Trun is here and Wolfram is here. Okay, yeah, it's actually very high. The citations are very high. So this guy actually from Germany. I think he was a professor in uh, University of Freiburg. Then he moved to Toyota Research, I guess. Let me check his current. Yeah, I think he is not updated. Yeah, he's having citation over 1 lakh. Uh, yeah, yeah. So these are the pioneers who actually, I mean, started the revolution for the self-driving as well, self-driving cars. Um Sebastian Tron, yeah, he's running Udacity, and also the Waymo he actually created. Waymo is created by it was not Waymo, it's a Google self-driving car division. He started, and I think he's not collaborating with Waymo now. Okay, so these are the, and Also, one of the key challenge was the um, DARPA challenge 2007. That is the DARPA Grand Challenge, which actually like this was the result. I mean, because of this challenge, only self-driving car got this much of attention, and also lot of research work happened specifically in the SLAM mapping and control area. Okay, so the DARPA challenge, there was two challenges. One actually won by CMU Carnegie Mellon. That was a first challenge, I think. Then there was urban challenge. So I think, yeah. So for the grand challenge, CMU actually won. For the next challenge, I think Stanford actually won. So this challenge, no, the robot has to autonomously move from one place to another. We can see some highlights, so you will get an idea. It's happening in 2007. Okay, so this is a challenge. Famous company are I mean famous companies and also the institutions. Um, yeah. So there is no people in the car. It's actually moving autonomously, and it's happening in 2007. So this is a Stanford team led by Sebastian Tron, and the robot is autonomously going. No one is here. It's going through the road actually. The first challenge was in a desert, but this is actually in an urban environment. It's an urban challenge. The Caterpillar, I think it was from CMU. So in 2007, these robots are performing much better, right? I mean, there is no one in the street, but still, in that time, with this technology and limitation in the sensor, they can perform this much better. So Tejas is having question, is a 3D slam is used. Yeah, I think a kind of 3D slam they are using because they have Velodyne. They have Velodyne, so they are using, I think, both 3D and 2D, and with the help of GPS, and also, yeah, I'm not sure, but there are I have done actually a literature survey regarding the DARPA challenge and all. So there are many papers available, case studies are available. So it's actually good to know like this much of people are working in this domain. Yeah. So yeah, this is Stanford. Stanford actually finished it, and the challenge is actually the cost, not cost. The price of this challenge is very high. It's in terms of millions. So that's why these um, companies and institutions are competing for it. Yeah. So this was the change happened. I mean, after this challenge, Google. So this person now, he's a very famous personality. This person, he's from CMU. I have seen him. His name is Red Whitaker, and I think he's 6 feet tall. It's very big guy. You can see here. Um, he's having a lab in CMU, and yeah, so he's working on different things. Currently, they are not working on the self-driving cars, but he's working on space robotics. So he's having a company as well. Um, so he's a pioneer in robotics, I will say. Red Whitaker. Yeah. So yeah, great. Okay, so that's it. So there are a lot of work happening in this area. Yeah, I think CMU won the challenge. I guess second place, I think. Okay. Yeah, I think that's it. So maybe next class, maybe tomorrow, we can start working on the SLAM algorithms. Today was basically an introduction about SLAM, what kind of SLAMs are available, and tomorrow we can start working on the SLAM on ROS, and then we can demonstrate each SLAM algorithm using Turtlebot 3. So that is a plan. And yeah, so if you have any doubts regarding the general aspects of the SLAM technology, let me know, so I can answer if I know already. Yeah, let me know if you have any questions. I think we can conclude for today because my voice is going down. Yeah, so if you have any questions, guys, just let me know. In the meantime, I can play some, yeah, some video. So this video, the tartan is actually from CMU. Tartan. So I think in that challenge, CMU Tartan. Tartan is the dog, I guess. I'm not sure. Yeah. So $2 million was the prize money of DARPA challenge. At that time, 2 million is actually very high, right? 2 million or 4 million, I don't know. Yeah. Oh yeah, it's the first place. Yeah, that's great actually, right? So any question, guys? Any question related to this? Let me know. Um, yeah, maybe I can play some more videos. You can also see in YouTube. You can see the sensors, right? Like here we are not using only one lidar. It's a combination of three lidar, 2D lidar on the front. And yeah, so there is a question from Tejas. You had mentioned about sensor fusion. Will we cover that as well? Um, so the sensor fusion, in the sense, like, maybe I can discuss that, because anyway we have to create a better odometry by sensor fusion. Uh, I was talking about the sensor fusion of the odometry, and but there can be sensor fusion for the camera and lidar as well. There can be. So I can describe that, maybe not in deep, but maybe I can discuss about it maybe tomorrow. Okay. Yeah. Yes. So I think we can conclude for today, guys. My sound is actually not very good. So yeah. So tomorrow we can discuss about different SLAM algorithms, and then yeah, the sensor fusion also I can discuss. Okay. So thanks for attending, everyone. See you tomorrow, maybe at the same time. Okay. Okay, everyone. Bye. Thanks for joining.